Reaction, also called 1,4 conjugate addition, is a way to add to a conjugated system a nucleophile. We've seen many examples of 1,2 addition where a nucleophile could add to ketone, aldehyde, ester, acid, etc. in what's called a 1,2 fashion. And something like that would depict what's happening, where the H could also be an electrophile. In a 1,4 addition, what happens is we have a substrate, also called a Michael acceptor, such as methyl vinyl ketone. Methyl vinyl ketone can be made by condensing acetone and acetaldehyde with appropriate catalysis. As an enone, and it's quite electrophilic, as are most Michael acceptors. Along with that tendency is they have a tendency to be toxic and not good for us. At any rate, using methyl vinyl ketone and a nucleophile, the 1,4 modality is a way to describe how the nucleophile and subsequent electrophile adds to the overall conjugated system, whether it be an enone, an enal, an enester, a cyanoacrylate, or a vinyl nitro compound. In this case, the nucleophile adds like so, generating a species like that, which can then pick up an electrophile, which is usually a proton. And then, as we've seen many times now, that tautomerizes to how we commonly show the product as a ketone in this case. So we call it a 1,4 addition again, because if we label that atom number 1, then that atom's number 4, and the two groups that we've added have come into number 1 and number 4, or number 1, which then tautomerizes to number 2, but it's still called a 1,4 addition. To be a good Michael donor, you have to be nucleophilic, and we've seen many nucleophiles. Some of them are just nucleophilic because of a lone pair. Some also has a negative. Recall the Gilman reagent, where we have a R as a nucleophile, and the R group is an organic carbon-based molecule. We also have enamines that can have nucleophilic carbons, and then we've previously described many types of enolates, say from beta diketones, beta ketoesters, malonic esters, simple ketones and aldehydes and esters. Of course, these would require the use of a very strong base like LDA, and a few new ones here. Actually, either of those two carbons would be easily formed in enolate because of the two electron withdrawing groups flanking what we call the alpha carbon. So we can prepare many enolates, and we can also add these many enolates to suitable Michael acceptors. And the characteristic of a Michael acceptor is again an ene conjugated to some carbonyl or cyano or nitro group. And again, we can add our nucleophile to that position now, and then the resulting electrophile onto those positions, and then likely tautomerization to give an overall 1,4 adduct. Classic example of that is in the Robinson annulation, which are ring-forming reactions. So if we take this cyclohexanone derivative, specifically 2-methylcyclohexanone, and our methyl vinyl ketone, after treating the cyclohexanone with LDA, of course, we're going to get an enolate centered around the alpha carbon next to the carbonyl, and the enolate in this case is going to attack the methyl vinyl ketone in a 1,4 sense, which would result in that species could be worked up and a proton put on the enolate form to make the enol, which of course will then be shown equivalently as its tautomeric form. If we treat that with another molecule of base like sodium methoxide, we can get the enolate formed off the methyl group carbon in this case, and then that is in close proximity to the ketone of our original cyclohexanone derivative, and we can make that connection, resulting in a typical aldol-like product, aka beta hydroxyketone. And these beta hydroxyketones, if mildly heated, of course, can dehydrate to the conjugated enone. And take note that this enone is again a suitable Michael acceptor, so we could do further reactions. And the Robinson annulation, which is what this is called, pays homage to Robinson, who developed this system of building up rings upon rings.